Welcome everybody to the only day of week 16. We're going to be talking more probability, more stats. We're also going to be talking a little bit about convex hulls today, as this will be your last Bridges assignment. So, first thing though, is I want to just show you guys how to zip things in Unix. So there's a command called tar. It stands for tape archive, and you're going to use it a lot if you go to a school that is Unix based. They typically have you submit your homework by tarring it and sending it in. I mean, there's lots of different systems, but you're probably going to encounter this. And if not, then when you start using Linux, you'll undoubtedly encounter it, either to create or probably more often to uncompress zip files. So they're not zip files, they're tar files. So this file here, tar, is the extension. It stands for tape archive, and it's basically like zip, okay? But it's not compressed. So tape archive is just all the files kind of put together, and there's a certain file format where it says this is this file, this is this file. There's a directory where you can kind of browse around inside of it if you want. And then you provide tar. So we're going to create, that's what the C means there. C means create. We use X to extract. So X would unextract from a tape archive, C creates a tape archive. V means verbose, and F means files. So tar CVF is your standard way of making it. You don't technically need the V. I always like seeing what files are added just to make sure that I did it right. You then provide the name of the tape archive. Don't forget that. Don't forget that. If you forget that and you do like tar CVF star.cc, the first .cc file is going to be the destination of your tape archive, and it's going to overwrite that file. And you will be a very, very, very sad panda. I did that once on a homework assignment and exploded one of my files that I was trying to turn in. Ooh, yeah, that was a terrible mistake. Fortunately, I did the homework early enough that I could just recreate it. But wow, yeah. So you then provide a list of folders and files that you want to zip. Typically it's actually files. You do like star.cc, star.h, makefile, that kind of stuff. And it zips up all the stuff. But I'm actually passing it to directories. One directory is what has been pushed out to all of you, called Bridges_Andrew. And that is your homework assignment, because I'm giving this to the Bridges people so they can have a copy of my homework assignment. It's got the README file and the demo files that I send out to you, all that stuff. And then it's got my implementation, which is in bridgesandrew.reference. So I hit that, and you can see the list of all the files that get added. Bridgesandrew, all the files. Bridgesandrew.reference, all the files. And then ls dash. Yeah. So we got a file there named bridgesandrew, and it is, let's do it in human readable format, 1.8 megs. Now I can do tar tvf bridgesandrew.tar, and if you do bridges tvf, that means test, and that just kind of shows you what's inside of a tar file. And so I can look at this and verify that there's two directories in there, and they've got all these different files in it, main.cc, and yeah, okay. So now that I've done that, I can do gzip bridgesandrew.tar. Yes, no, override the old one. And then ls-l bridgesandrew.tgz, tar.gzip. Sorry, tgz is the same thing. And you can see that it has dropped to 465K. So it compressed at about a bit better than 3-to-1 ratio. So this gzip compresses a file, and yeah, so it deletes the old one. So it actually removes the old file and puts a new one in its place by default. So now that I've got this gzip file here, I need to transfer the file off onto my computer here, and this is something all of you should do before the end of the semester or during finals week or something, where you back up all of your files. Okay, so use WinSCP or any SCP client. SCP stands for the Secure Containment Protocol. And what you want to do is connect using your same credentials username and password to the server, and then you can browse all the files you have on the server over here. This is your local directory, and bridgesandrew.tar.gzip is there, and I'm just going to drag that over, and it's going to replace the other one that I just had, and that is how you can back up things. So you could, just drag over all your files, that's fine, or you could gzip them up and send over a single gzip file containing all of your stuff. Okay, so now that's done, we are going to upload, and I'm not going to show you the URL for that because it's got all the homework solutions on it, but I'm going to file upload, bridgesandrew.tar.gz, update existing, upload complete. Okay, there we go. So there we go. So you want to go over the quiz first? Okay. So we'll hop back into Bridges Andrew in a bit. Let's talk about the quiz for today. And we will be continuing our discussion on probability and statistics. Combinatorics tie in with it as well. What are the odds that you guess the password right, given these rules for a password? It has to be, 5 letters long exactly. What are the odds you get it right on the first time? Yeah. Anyone want to take a crack at that one? I'm almost done with your proof by inductions worksheet. It takes a while to grade them. There's 29 problems. 15. And I don't want to do that one. I just want to do the stats. There we go. 63%, not good. All right. Roll a d6. What are the odds if you roll a second die, it'll be below the earlier die? Okay. So, so there's 36 outcomes, right? And there's half of them are in the upper half, meaning it's above. 6 of them are on the diagonal, meaning it's a tie, and the other half are down below. So out of the 36 outcomes, I did this wrong, didn't I? Out of the 36 outcomes, 6 of them are ties, and then the bottom half, it should be 1536, huh? Yeah, all right, I'll fix that. Okay, yeah, so the bottom half of the remaining, so out of the 6 are on the diagonal, and the bottom half is half of the 30, right? So maybe roll a second die, will be below the earlier die. Yeah, it's 1536. Good job. When it gets too complicated to figure out a probability by hand, I use Monte Carlo to estimate the odds. Cool. All right, let's just fix that right now. Edit. Negative. All right. Easy. All right. So yeah, you guys did it correctly. How many students we got here? We got 9 students. What happened to the rest of you guys? It's just everyone AFK or something? I don't know. Okay, so let's talk about the convex hull. So a convex hull is an important concept in a lot of different areas. Oh, my tablet got unplugged. It's used if you're doing like simulations, numerical optimization, 3D graphics, video games. So it is comes up a lot. So let's switch over into OneNote and come up into CSI 26. All right. And let's use the rainbow pen, why not? So let's say that you've got a bunch of points on a map. And let's say that you took a rubber band, and you kind of took the rubber band and kind of stretched it out. Like, let's say these things are like thumbtacks on a board. You stretched a rubber band out over all of them and you released it. The rubber band would snap down on these thumbtacks and make something that looks kind of like this, right? You guys understand? That, like, the rubber band would snap down and kind of stretch around the thumbtacks like that, right? Does that metaphor work for you guys? You can have more thumbtacks in here, it doesn't matter. Okay, so where it just pieces itself together. I don't know what that means. It's not a Veroni thing. It's what you're trying to do is get the points in out of all these thumbtacks that are on the outside of it. Okay. So you can have all these thumbtacks on the inside, and they don't really matter. Okay, at least for the convex hull. So what you're doing is you're adding edges between the vertices on the outer part, and the inner ones kind of don't matter. Even if I add more thumbtacks in here, it's not going to change the convex hull calculation at all. So there's a lot of different convex hull algorithms. They're really important in a lot of different ways. Like I said, these could represent like linear algebra, like mixing things, and which seems really weird and probably is. But I teach video games, so I'm going to talk about video games. So if you're that student that complains I talk about video games too much, well, guess what? This is called computational geometry, and it's a real serious academic environment. So academic endeavor. Where is my computational geometry book? Here it is. So here we go. Computational geometry. You got a graph, and I am a little bit salty about it. Yes. I mean, nobody said you're salty about it, but yes, I am salty about it. Because video games are fun, so who cares? But this is actually computational geometry, and so things like robot motion planning, and convex hulls, chapter 11. So there's an entire chapter in the book on convex hulls and doing things like if you've got a bunch of points and you want to wrap a 3D polygon around it to represent it, how do you do that? And so we're going to do the 2D version, but there is the 3D version's obviously used a lot as well. In Quake, if you look at the source code to Quake, the hull is the fundamental unit, really, in the engine. Source saltiness intensifies. Thank you. So let's see here. No, that's not what I want. I actually want to look at the server. There we go. Source code. So this is the actual engine source code for Quake 1. And math and assembly. Look at that. It's all assembly stuff. Load clip nodes. Hull. Make hull. Right? It's just, all over the place. Like, that's sort of the fundamental unit for doing the graphics and the rendering in it. Is they wrap holes around everything, and then they render them. And load faces, surface extents, load texture information, load edges, load submodels. so basically, what it does is that planes. Yeah. So don't show again. Go ahead. So basically, all the rendering that takes place, uses these convex holes. Okay. So how do we do it? What's the book called? Oh, it's a good book. It's a really good book, by the way. It's not the easiest book to understand, but it's a good book. You kind of have to. Sometimes you have to reread a paragraph a couple times to kind of get at what they're getting at. But it's actually pretty good. It's Mark DeBerg's computational geometry book, Algorithms and Applications. It's kind of the go-to textbook for computational geometry. And just whacked my monitor with it. And it goes over a lot of those topics, and things like what we're doing here is computational geometry. It's also graph theory. So, is this used for things aside game development? Yeah, like I said, if you're doing if these points represent different quantities that you're mixing together, like you've got different solutions, like in chemistry, that have different amounts of different components in them, and you want to mix them together, and you want to find out what mixes are possible. That's technically a convex hole as well. So yeah, they're useful. So how do we do it? How do we go from something like this? I'm just gonna throw some random points down. How do we go from this to having a hole, right? So there's actually there's actually a Wikipedia page called Convex Hole Algorithms, and there's actually a lot of them, and there's one that's kind of like the go-to best algorithm. The one we're going to do is not optimal, but it's pretty good. Can you see what connections are possible between the nodes on the outer layer? No, because they might not be hooked up, right? Like in graph theory terms, like it could be, it could be like this, right? They might not be even attached at all. So what you're doing for this assignment is you're going to add a red line like this between the nodes on the upper layer, on the upper hole, and then you're going to add a giant blue line like this on the bottom hole. And that's going to, so when you look at it in bridges, where are my bridges? Go. Unfortunately, the lines are curved. It's supposed to be a straight line, but whatever. You're going to be passed a map of cities in the U.S. and you're going to wrap them in a convex hole. And so this is going to define your national boundaries. I don't know. Okay, so we got all these cities in the U.S. and most of them are not on the convex hole. Most of them are interior, right? And so you color red the straight connections. And color no. The curved has nothing to do with it. That's just because Bridges always draws things curved. So I have mailed the Bridges people. Could you give me a straight line, and then that'll look a little more accurate. Because right now you can see there's things that are outside of the convex hole when they're not. Because if you had a straight line here, you would see they're all inside of it, but it's just a rendering artifact. So so the red is the upper hole and the blue is the lower hole, and then purple is where the red and the blue come together. So we're going to do a implementation called the Andrew Monotone chain algorithm, which to me is like the easiest to understand. There's a lot of them, and I for those of you that were online last night, I spent probably an hour or two going through the implementation of different algorithms to require you to do, and I ended up deciding the Andrew Monotone chain is the easiest. So what it does is it sorts the points from left to right. It starts at the leftmost point, and you'll see it adds 1 point at a time. It goes left to right. It just goes left to right. And it adds 1 point at a time. Then if it ever discovers a left turn, then it deletes the previous node out of it. And then it does the same coming backwards this way. So if you ever see a hook to the left, then the previous node, not the last one, but the one prior to the last one gets deleted. And that eliminate, and then you repeat. If there's still a left turn, you repeat the previous one again. You see that every time there's a left hook, the one previous gets deleted out of the hole. And what that does is it causes the hole to only have right turns in it. It's not an ambi-turner, right? It only turns to the right. And so you see every time there's a hook to the left, the previous node gets deleted, and it just adds one at a time, right? It's going to go through every single point, adding every single one of them. And I can't turn left. That's literally the Andrew monotone hole algorithm. You cannot turn left. If you ever have a left turn, you have to eliminate the previous person, the previous vertex, and do it again, because you might still have a left turn, and so you have to keep deleting people off the hole. You see how there's like people in here, and they're going to get popped off, you know. And you do that by just doing a vector, and you just push vertex after vertex onto the hole. And then if you ever discover a left turn, you pop off the last person and you check, do I have a left turn again? Yes, pop off the last one. Do I still have a left turn? Yes, pop it off. And you keep doing that either until you've got a right turn on the last 3 points, or you're down to just 2. When you're down to 2 points, you can't detect a right turn anymore, because a right turn is by looking at this line and then this line. Okay. If this line and then this line are right turn, you're cool. If all you had was 2 people left, though, you can't have a left turn because it's one line, right? 2 vertices forms one line. You have to have at least 3 vertices to have a left turn. And so yeah, so you could feasibly pop everything off and just have 2 vertices on the upper hole. That's the minimum you can have. So the algorithm starts by pushing the first 2 onto the convex hole, and let's see if I can actually screenshot this. This might be a good one to screenshot here. And so let's just go through it. First of all, do you guys understand like how I made the hole? Well, I didn't tell you how, but do you understand how this is a convex hole? Like if I just gave you a set of vertices, and the vertices have x and y locations, latitude and longitude. In this case, it's actually the latitude and longitude of the cities in the U.S. I feel like they really missed a chance when they named this algorithm. You don't like Andrew's monotone chain? We could call it Kearney's monotone lecturing style. How would that work? Yeah, so for every left, pop off the previous vertex. Kind of like Dijkstra's, where you have 2 different structures. In the case that the process is lost, you'll delete from the process. Yeah, so I end up having, I think 4 data structures. I start with a graph, and then I don't do anything with a graph. All I do with a graph is I turn it into a vector, and that's in your demo code. And so I copy all the points out of the graph into a vector. Okay, and it's just a vector of points. A point has an x and y location. I then sort it. So that's like step 1. I copy it out. I do that for you. Step 2 is to sort it, and you have to sort it left to right. Okay, sort it left to right, and then you have to write this. So there is a class called location that has an x and y location, a latitude and longitude, and you have to write the less than operator to sort it from left to right. Okay. Could have been blue steel. That's a fantastic name. That's a fantastic name. So you sort it from left to right, and then you start with the leftmost node. Okay. So whatever's that vector dot at 0, that's going to be part of the whole, and also whatever's here, because what we do is we first do the top, and then we come back and do the bottom. And so we sort it, do the top, we reverse sort it, and then do it again. So it's the same algorithm twice. One to do the top half, one to do the bottom half. Okay. And so I basically don't even need to tell you about the bottom half. It's going to be the same as this one. And so you start with the left node. So we'll start here. And then we add and then we're going to do this in a loop. Add I, vector I, to the whole, and then 5 check for left turn. Okay, I'll show you guys how to do that in a little bit. Basically, there's a function that I've given you called the cross product. The cross product tells you if something's a left turn or a right turn. Hey, you don't have to figure that out. Because I'm sure a lot of you were sitting there like, how do I tell if something's a left turn or a right turn? Well, for those of you that have taken game development, you would know, and it wouldn't be a surprise, because game development teaches you linear algebra and has useful stuff like this in it. Hey, who knew game development could be useful? But basically, you're going to cross product 0, 0.1, 0.2, and these are the last 3 people in the whole. So let's call this one 0.0, and then we've added this person here as 0.1, and then we've added this person here as 0.2. And so right now we've got a right turn. So the cross product is going to be negative. Negative means right turn. And positive means left turn. And a 0 means that they're collinear. So if you have a collinear point, I don't care whether or not you include it in the whole or not. I think I'd get rid of collinear points. It's very, very rare because you're dealing with floating point numbers, right? So, okay, so P0, P1, P2. Okay, and then if right turn, go to step 4. Okay, so we're good. So we start off with P0 and P1 basically in the upper hole. Then we add P2. So we say from I equals 2 to, n, right? Whatever the last one is over here. So we add it to the hole. Okay, looks good to me. It's a right turn. We move on to the next one. I is now 3. So 1, 2, 3. This one is now P3, let's say. So we add that one to the hole. And so what we do is we check to see, is there a left turn in the last 3 points? So we pass cross product P1, P2, P3. We get a positive number. That's not good. Okay? So if we get a left turn, we pop previous node. Arrow, 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 arrow. Not the current one. The current one's P3. Previous one's P2. Do you see how this guy is causing the problem? This is the troublemaker right here, right? So we pop P2. We delete P2. Okay? P2 is now gone. And now the last 3 are these 3. And then repeat. Number 5. So now we still have to check to see if there's a left turn. We're not done yet. We're only done when there's either 2 people left or it's a right turn. Yeah, I just pop back. I just call pop back. It's easy. So I don't actually, when I say I add vector I to the hole, I actually don't. I tentatively add it to the hole. So when I do the cross product, I'm grabbing hole dot at size -2, hole dot at size -1, and then this guy is not, I haven't actually added them to the hole yet. I just have grabbed, vector I. So I pass in hole, and then vector I. And then if that's a left turn, I just call pop back, and that deletes this one. And then I do it again. And so I sort of tentatively add it to the hole. I actually don't add it to the hole, so I can call pop back easily. The code's this big to actually do it. Like if you were watching last night, it took me half an hour to write the algorithm. And it's kind of a gnarly while loop. It's like while either the number of elements in the hole is greater than 2, and there's a left turn, call it pop back, and that's basically it. That's the heart. That's the heart of the Andrew monotone chain. And right here we have another left turn. You see that? So it's a very slight left turn, but it's a left turn. So we call pop back again on P1, and now we're down to 2, right? And so we're done. when you got 2 elements, you can't check for a left turn anymore, so you're done. So this guy has to be within the convex hull, at least for now. Okay. And then we add the next one, which would be this guy here, P4. Is that a right turn? Yep. A-okay. We then add P5. Is that a left turn? Ooh, that's a left turn. So we delete P4. P5 now. We add the next one, P6. And that's a left turn. So P5 gets deleted. And then we keep doing this. We're going to go through a lot of these in the middle here. But eventually we're going to get to like this guy here. It's going to be like P, I don't know, 20 or something like that. And, that's a left turn. And so that comes off. And you end up with that. And so the key thing here is you pop the previous one, and then you have to check again to see if there's a left turn. You can't just immediately go on to the next point. That's the key thing. Okay? Because you could have, feasibly, you can have like a bunch of left turn, guys causing left turns here, and you might have to delete that one, delete that one, delete that one, and then that's okay, because this is a right turn now. Right? So you have to keep doing the check for a left turn over and over again, popping, 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 until you get a right turn, or you're down to 2. So it's a gnarly looking while loop. It's also 3 lines of code. Ish. Whatever you end up with on the right side, that is in the outer layer. Yeah, when you get to the very end, the rightmost point over here, the rightmost point will be in the convex hull, and what you'll end up with is just the points. I just have a vector called upper hull, and it just holds all of the points in the upper hull, and then that's half of it. And then you do the same thing the other way. I don't know if you guys know about this, but there is the ability to sort backwards in C++. So you guys all know this, like sort vector.begin, vector.end. And in order for this to work, you need what operator for your, this is a vector of locations, x, y. You need a less than operator, right? Now, if you want to sort it backwards, there you go. Add an R before begin and an R in front of end. So sort vector, I'll write that out so it's not quite as, sort vector dot reverse begin, vector dot reverse end. Easy peasy. Sorts backwards. Yeah. So then I just sort it backwards and I do the same algorithm. Yeah. And it's still a right turn because if you look at the what we're doing is we're going clockwise, right? And so down here, this is also a right turn, right? You see that? We're going this way, and then we make a right turn. We make a right turn. We're not ambi-turners, right? So it's a horrible line. I don't even need to draw it because it's on there already. Okay, so right turn, right turn, right turn, and when you get to the left side, you're done again. So it ends up creating a loop that's clockwise, and that's actually really important. When you're making a hull, it's actually really important to know if, to have all of the points in a loop. And it doesn't matter if you do them clockwise or counterclockwise, you just have to be consistent. Right? Because, check it out, what can you do with a convex hull? Well, I would like to know if something is within a hole or not. That would be nice, wouldn't it? Knowing if something is within the hole. How do you do that? Well, cross product again. So if you want to know if this point here if you want to know if this point here is within the hole, given a hole, which is a bunch of lines like this held clockwise, what you do is you say, is this point to the right of this line? Yes? Cool. All right. Is it to the right of this line? Yeah? Cool. All right. Is it to the right of this line? Cool. All right. Is it to the right of this line? 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 Is it to the right of... If it's to the right of all of them, then it is in fact inside of the polygon. And that is how you can check to see if something is inside of a polygon for something more interesting than a square, right? Which is what people usually use. Right? So convex holes are very useful things. Like I said, come up a lot. So you're going to be writing a program to construct a convex hole. You're not going to be doing this. We could, but we're not. Take IS 50 if you want to learn how to do this. 50B. 50A is no programming, basically. Very little programming. Okay, so yeah, about half an hour coding. Then you have to do the bridges part. And the bridges part is pretty straightforward as well. You need to, no, not shaders. There. So what you're going to do is you are going to add to the graph. There is in fact a function called add edge that I wrote for you that you just pass in the name of the city and the name of the city, and it draws an edge between them. So, and you pass in the thickness, you pass in the color is a string. And so if you wanted to, no, not shaders, I haven't watched that video yet. I'm probably going to do shaders with my students. I don't know. We'll see. So CD bridges, Andrew. So there is this function here called add edge. You pass in the graph, you pass in the name of the first city, you pass in the name of the second city, you pass in how thick you want the line to be, and you pass in the color, which is a string. You can pass in red, you can pass in black, you can pass in purple, blue, whatever. The upper hole is going to be red, the lower hole is going to be blue. Okay, with a thickness of 3. It's in the README. You don't have to remember this. And so this function that I've written for you, add edge, you can find examples of how to do all this stuff in the code itself. It's a main.cc. You don't have to mess with main.cc at all. It's done. But if you want to find out how do I make a city bigger, because you're going to have to do this. How do I make a city bigger? You say graph, get vertex, you pass in the name of the city. All the get vertex things are basically, it's basically an unordered map hashed on the name, right? So you pass in San Diego and it gives you the vertex for San Diego. And then you call set size, set color. So for everybody in the hole, you're going to make the city bigger. And if it's in the upper hole, you make it bright red. If it's in the lower hole, you make it bright blue. And if it's on the leftmost and the rightmost, and these don't look like the leftmost and rightmost, but it's because we're on a globe, right? They're purple. Purple indicates they're both red and blue, right? Yeah. So for everybody on the hole, after you finish doing the whole computation, you're going to go through, set the size, set the color, and then you're going to make an edge between city 1 and city 2. Okay. That's just the name of the city. That's the name of the other city. That's the graph you pass in, and then you can optionally pass in like thickness of 3 and red or something like that. Okay. That's the add edge function I made for you. And yeah, so you don't have to worry about the details, the bridges details, mostly. There's one bit of bridges you have to know, and that's this. And there's demo code for that in main somewhere. All you have to do is look at the example and do it. Otherwise, just add edge. We'll add the edge for you. You don't have to mess with the data structure beyond that. And the code that I give you, so most of the work you are going to be doing is going to be in andrew.cc. There's one little bit of code you have to do up here. So here's our location structure. Holds your X and Y location. Latitude is Y, and longitude is X. So I've given you a cross product function, so you just pass in P0, P1, P2, and it returns a positive number on a left turn, a negative number on a right turn, 0 if they're collinear. Okay, so that's been done for you. You don't need to figure that out. I've got a double left arrow operator, so you can print a point to the screen. City name, latitude, longitude, all that's done for you. All you need to do is write this. So you're going to have to write a less than operator to sort the points from west to east. And if there's a tie, you sort... you sort on longitude first, and if there's a tie, you sort on latitude. So, least to greatest in both cases. So you do have to write that, because it's the kind of thing I want you guys to have practice doing. Really, it's not hard. It's just I want you to have practice doing it. I've put into the Andrew.cc. This is where you're going to be doing most of your coding. Andrew.cc has a static assert false in it. This causes the code to not compile. Okay, so as long as this is in here, your code will not compile. The reason why I do that is because let's look at the difference in error messages. Okay, so look at this compile time too, by the way. So I spent like an hour last night kind of refactoring, cleaning up, and moving all the code into Andrew.cc so you can get a faster recompile time. So right now it just says static assertion failed, make an operator less than. Okay, so it tells you what you need to do. The reason why I did that is because if I didn't, and you want to look at the error message we get, this is the first time you compiled your code, this is what you would look at. Because C++ has garbage error messages. None of this makes any sense. No match for operator less than. There's an error in predefined operations.h, and it doesn't even tell you, it's your code that broke, right? It's in predefined operations.h, line 43. Clearly the standard library must be broken. And you're like, all right. Right. So from Andrew line 1, like it doesn't even tell you which line the error's on. And that's a hell of a way of starting students off on this project. So I put in the static assert there. So rather than seeing this, which doesn't even tell you where the problem is, let's do that again. It'll just throw a static assert false. So just pull that line out. Okay. One thing you do have to do with main.cc is you have to put in your username and API key. So get those from the Bridges website and plug those in for the Bridges to work. But here's main. Main's pretty simple. Like this is the size of main. Sets up the Bridges object, changes the title to Andrew's Monotone chain. This is the graph. It's held in adjacency list format, so every vertex has essentially a vector of edges coming out of it. This function is written by the UNCC people, and it just loads a graph from disk. I didn't mess with it at all, I don't think. This they also gave me, which is how you overlay that picture of America on it, which is pretty cool. And then you write this code, Andrew. That's the Andrew monotone chain, Andrew for short. And then we visualize it. So that's it. That's the whole program. It's not bad. Technically, I think we can write this. Yeah. Have even less lines of code. And then .h, because I think, instead of our .h, we use namespace standard in Bridges, which is not good practice, but I don't care. So you just have to write this function mostly. You can see here I've got a vector of all the locations. That's all the vertices basically. So I go through the graph, and for every vertex in the graph, I add it to the locus vector. And the reason why I do that is because you can't sort the graph, right? The graph's not sortable. So what I do is I copy all the data out of it, put it into a vector, sort it left to right. Probably not the fastest implementation, but who cares? It's pretty bad. What's pretty bad? The error message. If there's only one or two people in the thing, technically, yeah, you can't have a hole if you only have two, right? A hole has to be a polygon. So yeah, the error messages are pretty bad. Yeah. So take this line out when you're ready to rumble. Okay. Don't just leave it in there. But it's in your demo code. Yeah, take it out. Sort it. And then after you sort it, the first thing you should do is this, right? Print it out. This is something I hammer into my students. Don't just assume something works. You know, like you wrote a function to sort it, print it out. See if it did in fact sort. You know, are you getting California before Maine? You know what I mean? Like, print it. You know, and so you can just print out all the vertices this way, just like that. Print them all out. See what you got, and then comment it back out again. Okay. And then you're gonna do the upper hole. You start off with you always have the minimum of 2 points in a hole, right? Yeah, you can't have a hole with 1 point in it because that's not a line. A hole has to have at least one line, so 2 points. And so you start off with 2 points in it, and then you're going to add 1 point at a time to the hole. Check to see if there's a left turn. If there's a left turn, you delete the previous guy, not the current guy, the previous guy. Check again if there's a left turn. If there is, delete the previous guy, not the current guy, the previous guy, and check again if there's a left turn. You keep doing that until either you're down to just 2 people in the hole, which is the minimum, right? Don't go below that. It'll explode everything. Either 2 people in the hole, you're done, or there's a right turn, you're done. Okay. And then you print it out. So this is going to print out all the vertices in the upper hole, and that's what the auto grader is going to use. I don't have an auto grader yet. I was up late last night coding this for you guys. There's no auto grader quite yet, but I'll put one together for you. And then you need to change the size of all of the people in the upper hole to be large, size 40, and change the color to be red. And then you need to add an edge between all the nodes in the upper hole. And that's going to create this thing here. So you're going to add an edge between all the nodes in the upper and an edge in all the nodes in the lower. And that's it. That's your homework assignment. You'll have a week to do it. Like I said, it's not bad. The algorithm itself is a little bit hairy, and it will explode your brain a little bit, but it's actually, you know, do over and over again. If there's a left turn, pop the previous guy until you're down to either 2 or there's a right turn. That's it. That's the algorithm. My for loop is like this long, but it's only like 2 or 3 lines of code. Yep. I was up late. Yeah, I'm ready for a nap. Okay, so any questions about this assignment? Should be a good exercise for you. It's within your Thursday, Thanksgiving. No, we're not open on Thanksgiving. We are going to do probably some gaming on Friday, 12 to 4. If you want to do Jackbox or something, we'll do that. The Betancourt was worried about the bridges side of this because there's a whole API you have to learn and stuff like that. And you know, there's examples in the code. The only thing you have to do is change the size and the color, and then use my add edge function to add an edge between the people on the hole. That's it. Okay. All the things in the middle you just leave alone. Now they did this with Dijkstra's. So they had this road network here, and they're based out of North Carolina, and so they made their city big, and then they Dijkstra'd from that. Of course, none of these were on the Dijkstra list because there's no roads in them in the graph. But they built a shortest path UNCC basically. And then they also did it again with a minimal spanning tree. Like if you had to design the freeway system between these cities, use a minimal spanning tree to do so. We're not doing that. Originally I had the Dijkstra's code in there, and then there'd be a little button down here and you can click to switch between the Dijkstra's and the whole, but I figured that would confuse you guys, so it just renders the whole. And I'm talking to them right now to see if we can get straight lines out of it, and then it'll look a little bit more like a polygon rather than I don't know what this is. Not a polygon, right? The whole point of the convex hull is you get a polygon like this, and that wraps everything. And then you can use the lines in the polygon to determine, are things inside of me, things not inside of me. Way to visualize on bridges for Markov. Close Thursday and Friday. Yeah. Mm-hmm. Yeah. Okay. So top hole, bottom hole are basically the same, just sort them opposite way. Cool. You can watch this animation a few more times if you want. Notice what happens every time there's a left turn. The black is the one we're tentatively adding. Well, we always add it, but it's the one we're kind of looking at adding. So every point gets added, because at every point it's the rightmost one that we've seen, and the rightmost one is always going to be in the hole. Now it might go away immediately on the next one, but you know, every point gets added as you go left or right. The black line there shows which one's being added. It's the previous person that gets deleted. Yep. And so this is a pretty easy algorithm, I think, in terms of all the different monotone, or not, all the different convex hull algorithms. So you end up with an upper hole that's in red, lower hole that's in blue, and that's it. There is code, in fact, in this thing. This is actually in your README file. We're going to look at the thing. You can look at the description. You can even look at the C++ implementation if you think that'll help you. And there's a cross product. There's the convex hull algorithm right there. If you think that'll help you. You know, that's it right there. So, sort them, and then lower hole, upper hole, done. So that's the whole algorithm. You got a week to do it. If you think this will help, knock yourself out. Plagiarize it as much as you want. Yep. I don't think it'll help that much, but maybe it will. I don't know. At least conceptually, stare at these 4 lines of code. This is the heart of it, right? Yeah. I don't do it this way. I use pushback. Okay. So let's go ahead and take a 15-minute break. Come back at 11:15. And if you have any questions, now's your chance, because there's no class on Thursday. So ask your questions now. All right, I'm going to go ahead and pause it now. All right, welcome back, everyone. I just realized that what I sent into the bridges people had .o files in it, which might be a little confusing. So I did a make clean, cleared out all the .o and executables and things like that won't help them. Then I'm going to re-tar it up, this time with no .o files. And then I will, again, gzip file bridges andrew.tar, and okay. So it is now only 66K, quite a lot smaller now. And I will once again copy it over to my local computer and then put it up on their site. So, did you guys come up with any questions? Because there is no class on Thanksgiving. You guys can be here, but I will not be here. I am here, but soon you will not be here, or something like that. So, there's a lot of homework assignments. There you go. Says like a 30 to 1 compression. Not bad. Not bad. 10. Yeah, about 30 to 1 in the gzip. Not bad. All right. So we'll do that, and then put it up on the Google Drive. I don't know if you guys got that reference. I am here, but soon you will not be here. Princess Bride, thank you, my man. Yes. So I will not be here on Thanksgiving. You're more than welcome to show up, but there's no class. Okay. Nobody has any questions about it? You guys all think you can do it? Okay. Sounds good to me. Bridges Andrew Tar.gzip uploaded version 3. All right. Good to go. I'll email them. Let them know that I've updated it. Okay. So let's get going on probability. Yeah. Probability theory. We're going to be talking about joint and conditional probability today and Bayes' theorem. Okay. Sending all of them. Okay. So, new symbols. Got some new symbols going on here, and the new symbols are. You need to do the assignment to know what kind of questions to ask. Plan on being in the office hours. Office hours are tomorrow. If you have any questions, so get cracking on it today, I guess. If not, help center. Okay. So, shift gears, no tricks, no weapons. Skilled against skilled alone. I think you have a slight advantage here. Yeah. Okay, so new terminology. Probability of x given y is written like that. The probability of x given y. So, let's say that I shuffle up a deck of cards, I pull a card up. And I ask you, what are the probability that I drew the ace of spades? I got a card right here in my hand. What is the probability? In fact, I got decks of cards right here somewhere. But whatever. Trust me, what is the probability that I got an ace of spades? Okay. 1 out of 52, right? There's 52 cards in a deck. If I shuffle it up, draw it, and ask you, what are the odds that I got an ace of spades? It's 1 out of 52. Now, I'm looking at the card and I reveal to you the fact that it's an ace. What are the odds that it's the ace of spades now? Right? I've just revealed to you some information. I've let you know something more about the thing. It changes the probability. Okay? So Cheryl is correct. It is a 1 out of 4 chance that it is the ace of spades. Okay, let's do it again. Shuffle up my imaginary deck of cards, draw out a card. I tell you, this card here is a heart. What is the odds now that it is the ace of spades? All you know about the card is that it's a heart. What are the odds that it is the ace of spades? 0. Yeah. Can't be the ace of spades. It's the heart. Okay. So, if it was a spade, it would be 1 out of 13. It's a heart, so it can't be the ace of spades. Okay. So, with conditional probability, it means you're going to modify the odds that something happened with additional information. So, for example, if we rolled 2d6, the odds of getting a 6 on the second die is 1 out of 6, right? It's a fair die, let's say. If you roll 2d6, what are the odds you get a 6 on the second die? 1 out of 6. Now, let's say I roll 2d6. I do have dice around here somewhere. And I roll it, and I'm like, oh, I got an 11. What are the odds now that I got a 6 on the second die? What do you guys think? How many different ways are there of rolling an 11? 3? Type them out. Type out all the different ways you can roll an 11. Five and a 6 and a 6 and a 5. Right? So if I reveal to you that I rolled an 11, the odds that the second die is a 6 is 1 out of 2. Okay. So, yeah. It restricts the probability. Now, if I told you the sum of the numbers was a 7, what is the odds the second die was a 6? So before I reveal any information, you had a 1 out of 6 chance of getting a 6. But then I rolled the dice, I look at it, I'm like, oh, I got a 7. What are the odds that the second die was a 6? One out of 4? How many different ways are there of rolling a 7? See that again. I rolled 2d6 and I got a 7. What are the odds the second die was a 6? How many different ways are there of rolling a 7? You guys remember? Six different ways. And so out of these 6 ways of rolling a 7, one of them has a 6 on the second die. Do you see that? So what we're doing is, rather than having this as the field of results, we constrain it to just these. Okay? So for conditional probability, it sort of constrains the field, and then you ask your question based on this. So what are the odds that any 6 was rolled if the outcome was 7? What are the odds that either the first or the second die was a 6? Was a 6? Yeah, 2 out of 6 or 1/3. So we got a 6 here, we got a 6 here. So if I reveal to you that a 7 was rolled, then there's 2 different ways you could do that. So we constrain, instead of 36 outcomes, there's 6. And we look at the 6 possible outcomes. Now let's say that I roll 2 dice and the sum is a 5. What are the odds that I rolled a 6? Zero. Yeah. If I rolled a 5, there's no way I could roll a 6. And so by revealing information, you change the probability of things. That's what conditional probability means. Okay? So conditional probability is you reveal information. So what is the odds of X given that Y happened? What are the odds that I rolled a 6 on either die if the sum total is a 4? 0. Right? What are the odds that I rolled a 6 on either of the dice given that the total is a 4? 0. You can't do it. Right? So if you have independent events, like if I ask you what is the odds that I get a 6 on the next die roll after I roll a 6 on the first die roll, what do you guys think? -1. So if I tell you I just rolled 7 6s in a row, what are the odds the next roll is going to be a 6? Yeah. Yeah, that's called the gambler's fallacy, right? The gambler's fallacy is like you can know something about the dice roll based on previous dice rolls. Now, sometimes that's true if you have a weighted die or something like that, or you have somebody cheating, they're doing a dice mechanic kind of thing, then sure. But if it's a fair die roll, and presumably most casinos are fair, then it doesn't make the slightest difference in the world, right? So if you rolled 100 sixes, the odds of getting a 6 again is 1 out of 6. Okay. So that said, sometimes you have dependent events. For example, when you have 2d6, the sum total is dependent upon the individual dice rolls and things like that. So the equation for computing conditional probability is this right here. So the odds of x given y is equal to the probability of x and y divided by the probability of y. The probability of rolling a 6 on the second die, given that you rolled a 7, is equal to the probability of x and y both happening, which is 1. There's one outcome where there's a 6 here. Divided by the probability that you get a 7, which is 6. Right, 1/6. So, or 6, yeah, there's 6 outcomes where the sum total is a 7. So, yeah, that is the algebraic way of doing it. I actually find just thinking about it, I think that thinking about it logically and kind of working through things intuitively makes math a lot easier than trying to memorize formulas. You know, like we talked about this last time. Like there's formulas for a lot of things, but I think you kind of work through it in your head and kind of understand how these things go. Right? Like for this question, right? What are the odds we got a 6? Okay. Well, there's 2 outcomes where there's a 6. There's 2 outcomes possible where there's an 11, and one of them has a 6. So it's the probability of x and y both getting an 11 and getting a 6 on the second one. It's 1 divided by the probability of y, and the denominators cancel out. So it's basically 1. There's 1 outcome out of the field of size 2. So it's a 1 out of 2 chance. Okay. So the probability of x given y is technically 1/36th, right? There's 1 outcome where you both get a 6 on the second die and you roll an 11. There's 1 out of the 36. And then how many times do you get an 11? There's 2 outcomes out of the 36. The 2 divisions by 36 cancel out. So basically, you just say, what is the size of the field? 2. How many of them has a 6 on the second one? 1. The odds are 1/2. 50%. Okay. To me, that's easier than working through the formula. But or rather, it's easier to learn a formula once you already understand it. That's always my approach towards mathematics, and you might have noticed that in this class. In the past, I try to avoid jargon and try and get you to understand the problem. Once you understand the problem and you've kind of worked through it a few times, then the equations become a lot easier to understand. Yeah. So let's try another one. What is the probability I get a what's the probability I get a ace through 4 if I reveal to you that the card in my, I just drew a card. What is the probability this is an ace, 2, 3, or 4? If I reveal to you that this is not a face card. It's not a jack, queen, or king. What is the probability this card here is an ace, 2, 3, 4? If I reveal to you this is not a face card. Face cards are jacks, queens, and kings. So what is the conditional probability? What is the probability that it is both divided by that, or you can just do it this way, which is honestly easier, where you look at how many the fraction of the field. Right? Yeah, 2/5 or 4/10. So if something is not a face card, there's 10 cards left, right? There's 10 cards. What are the odds that it's a 1 through a 4? 4 out of 10. 2/5. Okay. Does that make sense to you guys? If you did it this way, if you did the math, the odds of getting a 4 and it's not a face card is 4 out of 13. The odds that it's not a face card is 10/13. 13ths divide off because you have 4/13 divided by 10/13. The 13ths, the common denominators divide off. If you canceled, you end up with 4 divided by 10. Or 2/5. Okay, so joint probability. So conditional probability is what are the odds of x given y. Joint probability is what are the odds of both x and y happening, and they're kind of related, right? You see it right there actually. So the odds of both things happening is the probability of x and y. Okay, and so for independent events, you just multiply them, right? If I draw a card and then I reshuffle every time, each draw is a independent event, right? It's a dependent event if you draw and you don't replace, right? Because each time you draw a card, the odds change. I drew an ace, I drew an ace, I drew an ace. What are the odds I get a 4th ace? Anyone know? Shuffle a deck of cards fairly, pull an ace off, pull an ace off, pull an ace off. Wow, look at my luck. What are the odds that last card there, how many cards are left? 52 minus 3. There's 49 cards left in the deck. What are the odds that I pull the 4th ace like that? One out of 49. Yeah, pretty easy. And so the odds of getting 4 aces in a row like that is what? One out of 13? No. No, it's quite rare to shuffle a deck of cards and pull all 4 aces off the top. Usually that's a sign your deck is not shuffled, right? Or you're playing Magic the Gathering online and they built a physically based shuffler where they take half the deck and yeah, then you might get 4 aces in a row. What are the odds you ace, 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 just like that? How often is that going to happen when you do a fair shuffle? Or are you going to just pull 4 aces off the top? One out of 52 to the 4th power? Because remember, every time you draw a card, it's not. You would be right, Krente. If no, actually, no, you wouldn't be right. I know what you're getting at though. If you reshuffled every time, it would be a 4 out of 52 chance. You reshuffle, pull another ace, 4 out of 52, reshuffle, 4 out of 52, reshuffle, 4 out of 52. So it'd be 4 over 52 to the 4th power, right? Not 1 out of 52, because there's 4 aces, right? There's 4 aces. There's 52 cards. The odds of drawing an ace is 4 out of 52, or 1/13. So the odds of drawing an ace on the first one is 1/13 or 4/52, right? So the probability of 4 aces in a row, that's not really an equal. So the probability of 4 aces in a row is equal to 4/52, because the first card that you draw, you have a 4 out of 50 chance of drawing an ace. Then after it's gone, there's only 3 cards left out of 51. And after you pull that one out, it's 2 over 50 times 1 over 49. So that's the odds of drawing 4 aces in a row. The numbers go down every time you draw. It goes from 1 out of 13 to 1 out of 49. Okay. And so if we do the math here, the numerator is 24, the denominator is 52 times 51 times 50 times 49. So it is 24 out of 6 million. So it's 1 out of 270,000. Cool. Seems higher than I would have thought. Did I do that wrong? Maybe I think this might be the. Either. Okay. You guys see how that works? What are the odds that I roll a 10? What is the probability of rolling, let's say we have a 1d10, right? What is the probability of rolling a 10 5 times in a row? What is the probability, I have a d10, what is the probability I roll a 10 5 times in a row? Quintuple explosion in L5R. It's 1 out of 10 chance for 1. 1 out of 100 chance for 2. 1 out of 1,000 chance for 3. 10,000 chance for 4. 1 out of 100,000 chance for 5. Okay. So these are independent events, right? Independent events. Rolling a 10 a second time isn't affected by the first one. It's pretty easy. Use exponentiation. We went over this a little bit when we did combinatorics, right? So what is the odds if somebody, let's just say somebody has a password and their password is 6 letters, all uppercase, picked randomly. What are your odds of guessing it on the first try? What is the probability of guessing somebody's password when their password is 6 letters, all uppercase? And obviously you're only going to be guessing uppercase letters. You're not going to be guessing numbers and symbols and lowercase letters and things like that. What are the odds you will guess their password right on the first try? $36 over something. It's interesting. Yeah. Well, what are your odds of guessing the first password, the first letter? 1 in 26, right? So the odds of getting 2 right, if it's a 2-letter long password, it's 1 out of 26 squared. 3 right, 4 right, 5 right, 6 right. So the odds of guessing this properly the first time is 1 over 26 to the 6th power. Because it's a 1 out of 26 chance for each letter that you're guessing. The password is scuba. No, that's 5 letters. Scubas. All right. You have a 1 out of 26 in the first letter, 1 out of 26 on the next. So you might just get lucky. It doesn't seem very likely, but you could get lucky. Yeah, it's 126 to the 6th power. And if you want to compute that out, 1 over 26 to the 6th power, and we will invert that. So it is a 1 out of 308 million chance. You get it right on the first one. Go. Not that improbable. You get a botnet to do that, they'll get it like that. I read a report yesterday that when they try guessing passwords, they basically never try longer passwords. Only 9% of all password guessing attempts were more than, I don't remember what the cutoff was for a long password, like 10 characters or something like that. Somewhere in that ballpark. And so like the vast majority of password guessing attacks are for, small passwords or common passwords like soccer, password 123, hunter 2, that kind of stuff. So, I think you learned 8 characters. Okay. Yeah, this was yesterday. The report came out on it. yeah, 8 characters is plausible. So they almost never try guessing longer passwords. So if you just want to use a longer password, like, it'll help prevent you from getting password guessed, at least for common attack vectors. It's not going to help you against the NSA or something like that. When I was going to Sec Plus a few years ago, let me see if I can pull it up. An incident occurred. 77% of attempts use a password between 1 and 7 characters. A password over 10 characters is only seen in 6% of cases. Okay, there you go. So, yeah, use a password longer than 8. So if you have a password of 8 or longer, that reduces your chance. Like, they don't even bother, except 23% of the time. But then if you go out over 10 characters, then that drops from 23% of the time to 6% of the time. So, they'll just sit there and waste. They'll spin their wheels. Okay, so yeah, you're absolutely correct, Mr. McGon. Okay, so for dependent events, you might notice these things are defined in terms of each other. Look at that. The probability of x given y is equal to this divided by this, and if you just multiply both sides by the probability of y, you get this. So the same equation, you just multiply, you just move the term over to the other side. Right. So the probability of x and y happening is equal to the probability of x given y times the probability of y. So yeah, it's the same equation. Right. So here we go. I think, what does this add up to? 4, 5, 6, 7, 8. Does it add up to 1? I hope it adds up to 1. 4, maybe it doesn't. 4, 74, 86, 90. Yeah, it adds up to 100. Okay, good. So, what is the probability that we get event B1? So this is a diagram showing you the percentages, the different things happen. What is the odds that the event B1 happens? All the probabilities add up to 1. So the probability of B1 is not a trick question, it's 0.1. So there's a 10% chance. This is like your odds table, right? So you roll the die and there's different outcomes, things like that. Maybe B2 is like you get an even number, and B1 is like you get a 10 on the die, and like there's whatever. Like I don't know what they're supposed to correspond to. It's just kind of made up numbers. So the probability of B1 is 10%, right? So what is the probability of A happening? Probability of A. A is this circle here. It's not 0.3. It's bigger than that. Because these numbers are not inclusive. They're separate. 0.52, very good, this thing. So probability of A is 0.52. Okay. So what is the probability of B1 happening given we know that A happens? So before we had only a 10% chance of B1 happening. Now I reveal to you the fact that we know that A happens. So what is the change now? Now that we know that A happened, what is the odds that B happens now? 0.48. What is the odds that B1 happens if we know that A happens? What fraction of A is B1? Let's put it that way. If I were to color in the area of B1, you know, of size 0.1, you know, what percentage of 0.52 is that? Now you can't have a probability of 4. That doesn't make sense. What is the probability that B1 happens, given that we know that we're somewhere within here? We can disregard all these other people. They don't exist. We know that A happened. So this is the new field, right? This is the field of possibilities. We have this many outcomes that's B1, this many outcomes that is not B1 or B2, but A, this many outcomes that are B2. So this is the new field of possibilities. The denominator is going to be 0.52. The numerator is going to be 0.1. So the odds of getting a B1, knowing that we got an A, is 0.1 divided by 0.52. So that is going to be 0.1 divided by 0.52, which is 0.192. About a 19. Oops. Odds go up. Okay. So before I revealed to you that we're somewhere within A, the odds of B1 happening was 0.1. But now that I revealed, oh yeah, A happened. This we're in here somewhere, right? We're somewhere within A. Then the odds that B1 happened just skyrocketed, right? They almost doubled, because we know it couldn't be you, couldn't be you. So the odds that it was B1 go up. Now, if I revealed the opposite, if I revealed that it wasn't A, the odds would drop to 0, right? Because B1 is completely enclosed within A. Okay, so what is the probability of B2 given A did not happen? What is the probability of B2 given that our event is not in A? How many different total probabilities are there not in A? Add them up. That's going to be your denominator, right? Okay, no. It's not 0.7, because remember, this is not inclusive here. Yeah, it's 0.04 divided by 0.48. Right, because it's 0.34, 0.1, 0.04. That's the field now. We know that A is not happening. We can completely disregard A from existence. So the size of the field now is 0.48, and B2 takes place in 0.04 out of the 0.48, which is, was it 1/12, I think? Okay. 0.04 divided by 0.48. It's 1/12. Okay. So the odds go from 1 out of 25 to 1 out of 12. It's not bad. Well, no. I guess the odds of B2 before were 16. So it went from 16%, because we had a big chunk in here. It went from 16% to 8%, actually. It actually dropped, because most of B2 is inside of here. So the odds actually went down, but not to 0. Any questions about this? You guys think you can do this on your own? Let's do one where everybody responds. Okay, everybody. What is the probability? What is the probability of B2 given A? Same one as the last one we just did, except it's A instead of A complement. So I'm going to pause the stream for a minute, work through the math, don't type it out on the chat channel. In 1 minute, hit return. Okay. Let's see what you guys got. All right. Got different answers. Good. Means it gets to be a learning experience. Okay, the probability of B2 given A means if we know that A is true, then essentially we know that none of these could have happened. So our field of outcomes is 0.4, 0.52, and B2 represents 12 out of that 0.52. So the probability is going to be 6/26, 3/13, I think, is the odds. 0.23. All right, so you guys see how that works? So there's 12.12 possibilities within A. The size of A is 0.52, so this represents the fraction of 0.12 over 0.52. That's the fraction of B2. Okay, let's do another one. Again, I want to see everybody answering. What is the probability of B3 given A? I'll count to 20, type the answer. It's making for some exciting YouTube, let me tell you that. All right, whatever, hit return. Good, 0. Very good. Yeah, A happens, it can't possibly be B. All right, so probability B3 given A complement. So given that we know A can't happen, none of these. I'll pause the stream again, compute the probability that we get B3 given that A did not happen. And, all right, hit it. Okay. 0.1 over 0.48 or 1 over 4.8. So there's a total of 3.4, 0.1, and 0.04 outside the boundary of A. So the denominator, the size of the field is 0.48. Of that 0.48, there's a region of size 0.1. So the relative fraction is about a quarter. About a quarter of the outside area over here is found within B3. So 1 over 4.8 is in fact the correct answer. All right, so we'll do some quiz questions on that or something. And now we're going to get to the big thing, which is Bayesian probability. So Bayesian probability is a huge deal. It sort of is a different way of almost thinking of probability. Okay. Normally when we think of probability up till now, we've been thinking it in terms of what's called frequentist terms. In other words, how often do I roll a 7 on 2d6? Okay. How often do I roll an 11? How frequent is 4 aces in a row? Okay. So this guy by the name of the Reverend Thomas Bayes he said rather than figuring out odds, what we're doing is we're computing the degree of belief in a subject. So the equations are still the same, but you think of the probability almost in terms of like confidence. How confident am I that X happened given piece of evidence Y? Okay? And the equation's the same. It's the same equation we were just using before. Like, there's nothing different about the math. It's a different way of thinking about things. And so, for example, you might have heard of like a Bayesian spam filter. So Bayesian spam filter will develop a confidence that an email is spam. And it does so by presenting a piece of evidence after a piece of evidence. And every time you present an evidence, it updates its estimate that the email is spam. So you're like, hey, I found the word Viagra in it. Okay. The probability it's spam goes up, I found, your mom's name in it. Okay, the probability of spam goes down. And so on and so forth, okay? So you present it one piece of evidence after another, and when you get to the end of all the evidence, then whatever confidence level you have is the confidence level you have. And if the confidence level that it's spam is over some threshold, 90%, whatever, it's a tunable parameter, then you put it into the junk email folder. And if the probability is like 99.99%, you might just throw it away entirely and not even give the user a chance to look at it, which some email systems do, and it kind of annoys me because sometimes I get an email that's legitimate and it doesn't even go into my junk mailbox. It just gets black-holed. And that's a super annoying thing. Would this be using Markov chaining to accomplish it? It kind of feels that way, doesn't it? But no, it's the way that it works is this. You start off with something called a prior probability. And a prior probability could be estimated in a lot of different ways, but it kind of matters and it kind of doesn't matter. It matters a lot more when you don't have very much evidence. When you have a lot of evidence, the prior doesn't matter because the estimate will go up and down. Every time you present evidence, look, there's Viagra. Oh, it's spam? Goes up. Oh, it's from your mom. Goes down. Oh, she uses the word $, $, $. Okay, that goes way up. And so if you have a lot of evidence, the prior probability doesn't matter that much. But let's see if we have the... Okay. So you have the prior probability, and then you update it using what's called the posterior is after you have the evidence. So let's say you have a prior estimate that somebody committed murder. So you walk into a crime scene and you say, you know what, the odds that Mr. Smith committed murder was 1 out of 10. Okay? And then that's your prior. The probability X is the probability that Mr. Smith murdered his wife. Okay? And so you walk in there with some prior. And the prior can't be 0, can't be 100%. It's got to be some estimate. And you might walk in there like, it's like a 10% chance Mr. Smith killed his wife. Then you present evidence. And the evidence would be something like you found a blood-stained glove that matches his hand. Mr. Smith has tiny hands, and you find an extra small glove at the crime scene covered in his wife's blood. Okay. So what you do is you take your prior probability. Our prior probability would be, what did I say, 10%? Okay. 10%, 0.1. And you multiply it by what is the probability that we would find a bloody glove if he was the murderer that matches his size, divided by what are the odds we would find a bloody glove at all. And so, the odds that we would find a bloody glove that matches him, what percentage of people have extra small hands, right? And so the upshot of this is that if you have a quarter of the people in the world having extra small hands, then what are the probability you find a glove that's actually kind of small, And so the way the things work out is that you do the math, and maybe the prior estimate was 10%. Then after you find evidence that matches him, maybe the estimate that he committed murder goes up to 25%. Okay, and then maybe you find another piece of evidence. You talk to a neighbor, and they're like, "Oh yeah, Mr. Smith wasn't home that night." Okay, well you say, okay, what are the odds the neighbor would know that he was home or not? You know what I mean? And so if he was not home, what are the odds? And you do that, and you do that calculation, and we'll run through some actual numbers in a bit. You do that actual calculation and say, okay, well maybe, there's a good chance you'd miss it, so maybe it just drops a little bit. Then you find DNA evidence, and what are the odds you would find DNA evidence matching him if he was the murderer, divided by what are the odds? Then maybe that jumps it up to 90%. And so this is how Bayesian reasoning goes. Bayesian reasoning, as you present evidence to a claim, your confidence the claim is true goes up and down in response to, is it evidence for, is it evidence against? Okay. Are we talking about OJ? I don't think OJ had extra small hands, but yeah, sure. If the glove don't fit, you must acquit, right? So that's the high-level notion of Bayesian probability. Now, let's look at an actual example. And unfortunately, prosecutors either don't understand Bayesian reasoning. Let's see if I have an example here. No, I don't have it. Yeah, there's an actual case though where the prosecutors didn't understand Bayesian reasoning and were trying to falsely convict somebody because they didn't understand stuff. But let's get to that in a bit. Yeah, he couldn't get the glove on trial. It proves it. If you can't put a glove on during trial, that's it. You're innocent. It's just how it works. It's how our justice system works. It's like the sword and the stone. If you can pull that sword out of the stone, man, you're king of England. That's it. If you can't put the glove on, you're innocent. It's just how the justice system works. All right. So 1% of women have breast cancer. Let's say and 80% of mammograms detect breast cancer correctly. Right. If you have let's go through the probability tree. So there's a 1% chance you have cancer, the big C. It's also the name of a crocodile in Jacksonville. You have a 99% chance of no cancer. Right? 1% chance of cancer, 99% chance of no cancer. Probability tree, right? And then you take a mammogram. So the mammogram is 80% accurate. Okay? So if you have cancer, it'll detect the cancer. It'll report a positive case 80% of the time. It's accurate 80% of the time. It's inaccurate 20% of the time. So, and then if you don't have cancer, it detects it. If you don't have cancer, it detects breast cancer 9.6% of the time. So if you actually don't have cancer, so 99% of the time, you don't have it, but it will detect it 9.6% of the time. And that means the remaining, 90.4% is accurate. So you have a test case that's pretty accurate, right? The test case is pretty accurate. It's 80% successful if you have breast cancer. It's 91% successful if you don't have breast cancer. If you get a positive, what are the odds you actually have cancer? Okay. So here's the odds expressed a different way. So if you have cancer, 80% of the time you're going to test positive for it, 20% of the time you're going to test negative. If you don't have cancer, you're going to test positive for it 9.6% of the time, and you're going to test negative for it 90% of the time. If you guys just had to estimate that, if you got a letter in the mail, like my wife did, saying that she had breast cancer, which was amazing because she hadn't even taken a mammogram. That was fun, Kaiser just mailed out letters to 100,000 women saying they had breast cancer. That was cool. That was a nice little oopsie, you think that computer science doesn't have impact in the real world, they mass emailed people saying, you failed to... I didn't even know I took one. Yeah, thanks, Kaiser. So what do you think? What do you think if you get a letter in the mail saying you've got breast cancer? Let's say you're a woman, just for the sake of argument. What do you think if you just had to eyeball it? You have a positive test. You're positive for cancer. What do you think the odds are you actually have cancer? The letter's from your, whatever company you went to for the breast screening. You went to, I don't know. I don't want to come up with a wildly inappropriate breast screening place. We'll just call it Mammograms Are Us. There. Okay. So, except the R should be backwards. Okay. So you get a letter from MRU. It's a company that just does mammograms and nothing but mammograms. So you go in there, you get a mammogram, you come back, they send you a letter, you're positive for cancer. What do you think the odds are you actually have cancer? If you just had to eyeball it. You don't even have to work through the numbers. Just eyeball it. What do you think? No, don't do the math. Just eyeball it. Just, these tests are 80-90% accurate. You go in there, you get a mammogram, they say you're positive for cancer. What are the odds you have cancer? All right, so what we're trying to compute is what are the odds you actually have cancer given that you have a positive result. Okay, so out of every 100 people, there's going to be 0.8 people who have cancer and test positive. 0.1 times 0.8 is 0.8 people. There's going to be 0.2 people out of the 100 that have cancer but test negative. There's going to be 99 times 9.6. There's going to be 9.56 people who don't have cancer but test positive. And there's going to be 99 times 0.9, which is, I don't know, do the numbers. It's like 81 people that don't have cancer and successfully test negative. So, the relative chance that you have cancer given a test result that's positive is, here's the field. You tested positive. This is what you know. You tested positive for cancer. The odds that it's correct that you actually do have cancer is 0.8 over 9.56. So out of every 100 people that take this test, 0.8 of them will have cancer and will test positive. 9.56 of them will not have cancer and test positive. And so the odds that you are actually the person that has cancer are quite small. It's about 1 out of 10. Okay. So 0.8 divided by 9.56 is 8%. 8.4%. Which is really bad. Think about that. You go, you turn 40, you get your first mammogram, they send you back a letter, you have cancer. The odds you actually have cancer are only 8 out of 100. There's a 92% chance that you do not actually have cancer. You're going to freak out, you're going to panic, you're going to, sell off all your stuff and go to live in a monastery and start eating kale smoothies and stuff. But even after you get a positive test result from a test that's 80 to 90% accurate, you actually only have an 8% chance, 8.4% chance of having cancer. Now, it went up, right? Your prior probability, like just given the population of women as a whole, it's 1%. You got a positive test, so your probability of having cancer went up to 8.4%. Okay? So your odds of having cancer went up after the result of a test, it's still far, far more likely that you do not have cancer than you have cancer. And so this little tidbit here has been used by prosecutors to convict people wrongly of crimes, right? Let's say that this case took place in LA. Yeah. Layout blank. Thank you. Okay. Let's say they have a database. Let's say you have a database of everyone's DNA. Okay. So let's say there's a DNA test, and it is like 99.99 whatever percent accurate. Accurate. 1 in a million chance of an error. However many nines you need there to make it 1 out of a million. It's an incredibly accurate test. Okay, so how many people live in LA? $10 million? Easy round number. Okay. Population of LA? 10 million. Let's say that the database that the prosecutor's office has in LA has the DNA of every citizen in LA. And they arrest you, and they say, we're arresting you solely because the DNA test says you are guilty. That's the reason why they arrest you. They throw you in jail for the murder of somebody, and they present the evidence before the jury. Jury, there is a 1 in a million chance this test is wrong. This person must do it. This is beyond the level needed. It's DNA evidence. You've seen it on TV. DNA tests are incredibly accurate. This person's DNA matches the DNA at the crime scene with the 99.99, however many nines you need to make a million, 6 nines or something like that, to make a million. That is beyond the standard needed, beyond a reasonable doubt. That they were guilty of a crime. What are the odds you're actually guilty of a crime? If this is how they did it. They scanned the database of everyone's DNA, picked out you because your DNA matches the DNA found at the crime scene, and arrest you, try to send you to death row. What are the odds you actually committed the crime? This is not a hypothetical, by the way. The prosecutors actually do this. The odds you committed the crime is 99%. Okay. Anyone else want to spitball an odds on that? What are the odds you're actually guilty? Anyone else? McCohen? Just spit on a number. I'm asking you to guess. You don't have to have, real numbers. It's 99.99999% accurate. Your DNA test matches the blood found at the crime scene. You're clearly guilty, right? Anyone? Yeah, let's say 1 out of a million chance of an error. So, here's the thing. Your odds of you actually being a murderer is about 1 out of 10. The reason for that is because in a population of LA, which has about 10 million people in it, whatever it is, it's a nice even number, we'll go with that. That means that on average, you're going to get 10 errors, right? Now, the odds that it picks up the guilty party, assuming they're in the database, which we are for this exercise, they're probably going to be hit. This is actually not quite exactly 10%, because there's a possibility the actual murderer had rolled that 1 in a million chance and did not get picked up in the sweep. But basically, if they picked up everybody in LA who matched the DNA hit, that'd be 10 people on average. The expected value is 10. And so if they just arrested the first person that matched, 1 out of 10 chance that they actually got the murderer. And they've done this before. On no other basis than just a sweep of a database. And, oh, there's a match, bring him in. And then they'll go in front of a jury and say, look, the odds are 99.999% accurate. And it's up to the defense to say, no, the odds are 1 out of 10. Because y'all don't understand Bayesian reasoning. And unfortunately, there tends to be very little in the way of consequences for prosecutors to do this, right? So Aaron, do you understand? The probability you're guilty given a positive test is equal to the probability that you're guilty is X, given a positive test, is equal to the probability that you're guilty, which is 1 out of 10 million. The probability of guilty, the prior probability is 1 out of 10 million. The probability that you are that you have a positive test, given that you are guilty, is the probability that you get a positive test if you were guilty is like 99.9999%. 0.999, close enough to 1. Not quite. Divided by the probability of a positive test. Yep. And so what happens is the positive test is point whatever. And so anyway, so the when you do the math, you work it out. The probability that you're guilty, given a positive test, goes from 1 over 10 million. It goes from 1 over 10 million to 1 over 10 when you do the math on it. Okay, so it definitely goes up. Like if you get a positive DNA match, the odds that you are the murderer went from 1 out of 10 million to 1 out of 10. And if you get a negative match, the odds that you're the murderer drop substantially, because it'll go down probably to some really trivial factor. But it's still not even probable. It's not even close to probable. Okay. So, yeah. So, in situations like this, they will actually. It's a known problem. Like doctors, at least, are better at this than prosecutors, because prosecutors, there's no consequence. With doctors, they're aware that, like, if you tell somebody they have a positive result on a cancer test, that people are going to freak out. So a lot of times they'll just be like, we want you to come back in and do some more diagnostics. We're not sure. We saw something. We're not sure. Come in. We'll do some more tests. And like you'll get an MRI, or you'll get, a CAT scan or something like that. And they'll keep doing tests until the odds are probable that you have cancer, right? You can't just do one mammogram and be like, oh, they got positive, got cancer, right? Mammograms are almost like a screening tool, like to just see what group of people, because out of the original 100, 10 of them are going to test positive, thereabouts, and then you bring those 10 people in and you screen them again, until you get to like the person that you're probably is pretty sure is cancer, and then that's how the process works. Okay, so so that is Bayes' theorem. Let's go through some of the math on it, maybe. Save. Actually, I have some in the worksheet. That's funny. Yeah, the Wikipedia page has like a neon sign with it. Okay. So the probability of A given B is the probability of B given A times probability of A divided by the probability of B. So, go away, Wikipedia. So yeah, so Bayesian reasoning and Bayesian interpretations of probability is more like confidence rather than frequency. You know, how confident you have cancer. You know, it's different from like, you know, frequency. Degree of belief, yeah. Probability is a degree of belief. So it's a different way of thinking about things. So you start with a prior, which is your initial degree of belief. Somebody's a murderer, you have cancer, whatever. And then you update it with evidence. What is the probability of A given the evidence B? That's posterior. And then this thing here is what you multiply the prior by to update your thing. Okay. And so yeah, decision tree is one way of looking at it. All right. All right. So let's look at the worksheet. You guys have any questions about that? You probably should. There's been nothing said on the Discord for 7 minutes. So I call it Bayes' theorem. Master theorem. There you go. So the probability of x given y is equal to the prior probability times this thing here. So, for example, if x is there is a dangerous fire going on, okay, and y is there is smoke. So the odds, you know, if you just look around you right now, probably the odds that there's a dangerous fire in the next room over or whatever is probably pretty low. Like the prior probability there's a fire going on next door to you, pretty low. But let's say that some evidence comes in. You smell smoke or you see smoke, right? It just intuitively, like you should know the posterior probability that there's a fire going on leaps up, right? It's not 100%. It's not 100% because, you know, somebody could be cooking. There could be a wildfire out in the Sierra Nevadas as usual during the summertime. So just because you smell smoke doesn't mean there's a fire, you know, like next door to you, right? But the odds that you have a fire going on next to you go up, right? So we know the dangerous fires are rare, 1% chance, let's say, but smoke is common. You know, people barbecue, you know, a fair bit of the time. But we also know that 90% of dangerous fires make smoke, so the odds that there is smoke given that there's fire. So the odds that there is smoke given that there's fire is 90%. It's actually higher than that, but I'm just trying to make for even numbers here. Then, given these numbers, right, what's the prior probability there's a fire? 1%, very small. How often do you see smoke when there's not a fire? 10%. You know, let's say there's barbecues and things like that going on, or there's fires up in the Sierras, you know, that kind of stuff. 10% is probably pretty accurate for Fresno. 30 days in the year you smell smoke when you're outside. Yeah, sounds about right. Yeah. But you know, if there was a dangerous fire next door, you'd have a 90% chance of smelling it. The other 10% of the time, it probably is too early in the fire, you know, to smell it or whatever. So here's how you do the math, okay? So the math is the prior probability, 1%, times the probability that there is smoke given a dangerous fire, 90%, 0.9, divided by the divided by the chance that there is smoke overall, 10% of the time. Okay, and so if you do the math, the 0.01 times 0.9 divided by 0.1, it works out to 9%. Okay, so the odds that there's a dangerous fire, you go, I smell smoke. The odds that there is a dangerous fire nearby go up from 1% to 9%. So I'd like for you guys, and then we'll call it a day, to figure out the prior probability, figure out the odds, same thing, but the prior probability is 0.01% of the time. So it's very uncommon for there to be a house fire, right? 0.01% of the time. But 99% of the time, dangerous fires make smoke. So this number is going to change from 0.9 to 0.99. This number is going to change from 1 to 1% or 0.01 to 0.001. Plug and chug. Let's see if you can do it. I'm going to pause the stream. I'll give you guys a couple minutes to do it, and we'll come back. All right, begin. All right, so it looks like some of you were mixing up the probabilities and the percentages, right? So 1% is the same as 0.01. And 0.01% is 0.001, right? 0001. Percentage is divided by 100, right? So add 2 zeros to that. So the ratio, which is the quotient kind of thing here, this part of it. So our prior is going to dip by 100th, right? So it's actually 100 times less likely than before. So that's going to go down by a factor of 100, this number here. And then the quotient here is going to go up because we're making it much more likely that there is smoke from a dangerous fire. So before, there was a 90% chance of having smoke if there's a dangerous fire. The odds of there being smoke in general is still 10% because we're in Fresno. So what's going to happen is this is going to be 0.99 or 99%. This is still going to be 0.1 or 10%. So the ratio there is 99% divided by 10% is 9.9 times. And so the prior probability is 0.01%. That's going to get multiplied by 9.9 and turn into about 1%. Thereabouts. It's going to be 0.99% or 0.0099. All right. Make sense? So this number is that, right? And you multiply that by 9.9, and let's see if I'm doing the math right. No, it's 0.0099, right? Okay. Or 0.99%. Yeah. Yep. Not 10%. I don't think. Right. 0.01. We had a 1 out of 10,000 chance. 1% is 1 out of 100. 0.1% is 1 out of 1,000. 0.01 is 1 out of 10,000 chance. So we multiply that by 9.9, so it's now 9.9 out of 10,000 chance. So like that. Okay. All right. So then let's look at the cancer screening one again. This is the same as what we did in the slide with different numbers in it. Okay. So one easy way of thinking about this is to just think about if there's 100 people, how many of them test positive correctly, how many of them test positive incorrectly. And so given a positive test, what is the relative ratio that it's an accurate positive test versus a negative positive test? Okay. So X is you have cancer, Y is you tested positive for cancer. So the prior probability of X is 1%. 1% of all people in the population has cancer. The probability that you have, that you test positive The probability that you test positive if you have cancer is 80%. So in other words, the test is 80% accurate if you have cancer. The probability of Y if you don't have cancer is 10%. So that means the probability that it says you have cancer if you don't have cancer is 10%. So it gives you a false positive 10% of the time, or it's 90% accurate if you don't have cancer. So the probability that you have cancer given that you have a positive test is equal to 1%. That's the prior, right? The prior probability is 1%. You update it using this quotient here. And so the probability, so the quotient is the probability that you tested positive if you have cancer divided by the probability that you test positive. Okay. So the probability that you test positive if you have cancer is 80% divided by the probability that you test positive. And the probability you test positive is the total number of true positives and the total number of false positives put together. And so you add those together to get the divisor, do the math, and so the odds that you have cancer is only 7.5%. So if you have a test that's between 80 and 90% accurate, you get a positive test result, the odds that you have cancer is only 7.5%, depending on the accuracy of the test. And so you'll hear people say, this test is 90% accurate. Well, cool. Cool. So that means out of every 100 people, 10 of them are given a wrong result. You know? And so if cancer is just not that common, then there's going to be far more false positives than actual positives. And it's really bad for like rare diseases, right? Like if you're talking about some rare genetic disease that affects 1 out of a million people, even if a test is 99% accurate, out of every million people, 10,000 of them are going to test positive for it. And 1 of them will actually have it. So if you screen the whole population for some genetic condition, even if your test is 99% accurate, 9,999 out of 10,000 people is going to get out of the positive results are going to be wrong. So even though it's 99% accurate, it's the answer is going to be 99% wrong, 99.999 wrong. Okay, you guys see that? That's why we don't do broad screening of a lot of things, because no test is 100% accurate, right? I mean, yeah, maybe there's one, but error is part of science, and so doing things like broadly sweeping across all the people. Now, if somebody presents and they've got all the symptoms of the thing, then you give them the 99% accurate test, and if you get a positive, then you probably run it again or do a second test that isn't the same as the first, and to really confirm that they have it. That's why diagnosis is difficult in medicine, because there's a lot of false positives. There's, for rare conditions, you're going to get way more false positives than you're going to get actual positives. And that's one of the reasons why doing a dragnet in policing is so dangerous, because you can just scoop up a bunch of people and then, all right, where's your alibi? Oh, you don't have one? All right, off to jail with you. You can just grab all the people you don't like in town and charge anybody who matches some arbitrary criteria. Okay, so do you guys have any questions about Bayes' theorem? You want to do one more? Or do you guys want to call it? There's just been dead silence on Discord since I've introduced Bayes' theorem. It's a really powerful way of thinking about the world. It's a very different way of thinking about the world, right? But if you think about it, it's actually the path of rationality, right? The path of reason. A lot of people are 100% confident in something or 0% confident in something, and that's kind of irrational. If you're 0% confident in something, if your prior is 0, if your prior probability is 0, the rest of it doesn't matter. 0 times all this stuff is 0. And so no matter what evidence comes in, if you think there's no possible way that Joe Biden was elected president of the United States, then it doesn't matter what evidence you present, you will never believe that Joe Biden was, elected president, honestly. Right? So in any confidence levels of 100% and 0% are dangerous, because that means you're essentially immune to evidence. And so a rational critical thinker, you might say it's very confident or not very confident, but you're like 99.99% certain of something. But even still, that leaves the room for evidence. So if evidence comes in contrary to your view, you run through the math and then, okay, it goes down or it goes up, whatever. Okay. So this is like philosophy almost, like what does it take to know something? In science, we typically say 95% confidence is the cutoff. So if you're using a frequentist interpretation, that means if you run this experiment 20 times, once you would get this outcome due to chance, the other times it's a legitimate outcome. And so typically that's the threshold used in a lot of the sciences, is a 95% confidence threshold. There's a 1 out of 20%. 1 out of 20, not 1 out of 20%, 1 out of 20 chance this experiment's wrong. Right? And we just accept that. That's the level of standard for publication. If your odds that the thing you're publishing is due to chance is below 5%, you can publish. If it's above 5%, then you need to doctor the numbers until you get it below 5%. Which I joke, but no, what you do is you run more experiments. And the more experiments you get, the more confidence you have. But the Bayesian approach, the Bayesian interpretation of that is that I'm 95% confident in this result. So I have a high degree of confidence that this study is correct. And if I have a 99% confidence level, then I'm even more confident this study is correct. And so it's just kind of a different way of looking at the world from the frequentist interpretation, which is like there's a 1 out of 20 chance this is wrong, to the Bayesian interpretation, where it's just like I'm pretty confident this is correct. And if it's 99.999% confident, then I'm extremely confident this is correct. So, all right, I'll stop torturing you. I'll put up some quiz questions, and if you guys get it wrong, then we'll just hammer it more next week. Next week's the last week of class, so we do need to get on to statistics and things like that. But we'll see how you do on the quiz on the joint conditional and Bayesian probability. And enjoy Thanksgiving. Have fun. Work on the monotone chain algorithm. Shouldn't be that bad an assignment. And just ask for help on the help center. Don't wait to the last minute. I'll go to bed early on Monday night. So have fun with bridges. Yeah, I think so. I think you should be fine. For the Markov one, it was a lot more of bridges. For this one, like the amount of the bridges API you have to know is pretty minimal. There's example code for all of it in the code already. There's a function to add an edge, and there's example code in main.cc that shows you how you can change the size and the color of a city. So it's mostly just the algorithm. I just want you guys to do a convex whole algorithm because it's a fun algorithm. It's good. It's working a little bit with graph theory. And it's a useful thing to do. Okay, so yeah, it's okay if your brain hurts a little bit after looking at Bayes' theorem. It's normal. It's normal to have your brain hurt a little bit. All right, so we'll leave it there. All right, thanks, you guys. See you guys next week. Have a good Thanksgiving.